Welcome to This Explainer. Today we're unpacking a wild story about how an ingenious piece of space tech solved one of the biggest earthly mysteries of our time.
Let's kick things off with a seemingly impossible question. How exactly do you track a global resource that is completely invisible? We're talking about something you and I rely on every single day to drink, to grow our food, literally to survive, yet we can't even see it.
That invisible resource, it's groundwater. And get this, it makes up a staggering 30% of the world's entire freshwater supply. It's just sitting there in the dark, hidden away in pore spaces and rock fractures hundreds of meters below our feet. We can't see it, but our modern world absolutely runs on it. And the demand for it is just unprecedented. Roughly 70% of all the groundwater we withdraw across the globe is used strictly for agriculture. In fact, about 38% of all irrigated land on Earth relies on it. It is literally the most extracted resource on the planet, quietly pumping life into the crops that feed all of us.
Now, this water is trapped in these massive geological formations called confined and unconfined aquifers. Think of them as giant underground reservoirs. For decades, the absolute only way we could monitor them was to go out, physically drill a well, and drop a line down to measure the water level locally.
But you can probably guess the problem there, right? That hyperlocal, hole-in-the-ground approach left us with a massive blind spot. Because we couldn't see the total volume of water on a large, continental scale, we usually only found out we were running out when it was way too late. We're talking catastrophic stuff, family wells suddenly running dry, massive land subsidence where the ground literally caves in, or local ecosystems completely collapsing.
Then came a total game changer. Scientists asked this wild, totally out-of-the-box question. What if we didn't use normal cameras to look for water from space, but instead used gravity?
Enter the GRACE mission. That stands for the Gravity Recovery and Climate Experiment. It was a joint project between NASA and the German Space Agency running from 2002 to 2017, and later followed by a successor called GRACE-FO. This was huge. It fundamentally flipped our approach to hydrology on its head, giving us the very first and honestly the only observation-based method for tracking water depletion right from space.
The way it works is just a brilliant orbital dance. GRACE was essentially two identical twin satellites flying about 220 kilometers apart in low Earth orbit. Now, when the leading satellite flew over a massive concentration of water underground, and remember, water is heavy, it has mass, that extra gravitational pull would cause the satellite to accelerate just a tiny bit. Then the trailing satellite would feel that exact same pull moments later. Scientists continuously measured this minuscule change in distance between the two. We're talking literally a fraction of the width of a human hair, and used it to map the Earth's gravity field month by month.
Okay, so how do we actually get from gravity to groundwater? Well, the satellites measure what's called total water storage. To isolate that invisible groundwater, scientists use a clever equation of elimination. They take the total gravity signal, and then they subtract the modeled surface water. They subtract the snowpack, and they subtract the soil moisture. Whatever is left over, boom, that residual number gives us the exact change in our hidden groundwater. Now keep in mind the scale we're dealing with here. GRACE isn't zooming in on a single farmer's well or your local duck pond. The resolution is inherently coarse. It maps data on these massive 300 to 400 kilometer grids. We're looking at chunks of land roughly 150,000 square kilometers at a time. It operates at the scale of entire aquifer systems, massive river basins, and whole countries.
Section 1. Global Hotspots. The Invisible Crisis Made Visible.
With this new cosmic vantage point, GRACE started revealing a pretty staggering picture of what was happening right beneath our feet. Take India, for example, the world's largest groundwater user. GRACE exposed that northwestern India was losing a mind-blowing 18 cubic kilometers of groundwater every single year between 2002 and 2008. This was a massive, entirely unsustainable loss that completely challenged the older, local estimates based on spotty well records. And you know what? Making this space-based data public actually forced some real, immediate policy responses over there.
We saw similar real-world impacts right in the US too. Look at California's Central Valley during that intense drought from 2012 to 2016. GRACE picked up an astonishing 30 cubic kilometer loss in water storage. Farmers were just forced to drill deeper and deeper to make up for the lack of surface water. Having this undeniable objective data from space actually contributed directly to California passing its first ever statewide groundwater regulation back in 2014.
And the sensors kept finding these extremes. They tracked severe depletion in the Middle East,
where the Tigris-Euphrates basin lost roughly 144 cubic kilometers of water over a decade. But hey, it's not all bad news about depletion. GRACE also captures the healthy heartbeat of the planet. For instance, it can clearly detect the massive 1,000 cubic kilometer seasonal water pulse of the Amazon basin, shifting between wet and dry seasons. It's even tracking the sheer loss of 280 billion tons of ice melting off Greenland every single year.
All these observations eventually lead us to a pretty stark realization. As remote sensing specialists have pointed out, finding out that many of the world's major aquifers are being depleted way faster than they're replenished, well, is truly one of the most consequential environmental discoveries of the 21st century. It really highlights the incredibly fragile state of our most vital resource.
Section 2. Beyond depletion. Forecasting risk.
The coolest part? GRACE doesn't just show us what we've already lost. It's actually evolved into a ridiculously powerful tool for predicting future risks. By looking at all these water storage components together, we can practically see into the future. I mean, months before plants even show visible stress on the surface, GRACE can flag a deep subsurface drought. Or before a major storm even makes landfall, it can look at how saturated the ground already is to warn us about catastrophic flood risks. And when you look at it over decades, it gives us this crystal-clear, data-driven picture of shifting global climate patterns.
Thanks to a pair of satellites doing a continuous dance in orbit, we're simply no longer flying blind when it comes to our planet's hidden hydrology. Thanks so much for joining me on this explainer today. I'm going